first off, any specific questions from homework that maybe? Yeah.
7.3, 126.
Cool. So what part of this gave you trouble?
I'm just trying to look at the example, and it was a little bit different, so I was trying to figure it out, like, how I could do it without making the wrong answer.
So one thing to realize is I can't do 4 minus 11. I can't do that. It's not even up there. It's not anywhere that it says that. It doesn't say that. It says 4 minus something, right? Because the last thing I'm going to do up here, of course, is that subtraction.
You have to distribute first.
Exactly. Got to distribute first. The next level of mistake students make is something I don't think we would make yet, because we haven't talked about FOIL method yet. You guys might not. You're like, is that for baked potatoes? Well, that would be like where you're at. But all that's multiplying. What's the only thing's multiplying up here?
11,
11 and this thing. Right? In fact, negative 11 and this thing. So that's the next. So I'm going through all the mistakes that people can make. The next mistake is they forget that the negative's got to go with it. So the 4 is just sitting there waiting. And then what happens when they bring the negative 11? Negative 11 times 3c is?
negative 33.
Negative 11 times negative 2?
Positive 22.
And then you just combine any like terms. And what are the only like terms?
4
and 22. I like it. See how? A few people are looking at me like I'm crazy. I'm used to that. Alan, what's up? Say again? So what am I multiplying? So let me do it like this. Here's 3c minus 2, right? There's 3c minus 2 just sitting there. This problem kind of does this to it. It multiplies it by negative 11. And of course, what property? They tell you the property use, but we know this is going to be distributive property. Yeah, negative 11 times 3c is negative 33c. Negative 11 times negative 2 is plus 22. And there was a 4 in front, so there's a 4 in front. Is that cool? Did I hit on the mistake you made somewhere in there? Yes? Okay. So it's really good to see the mistakes you could make and then to see why they don't make sense, so you don't make those mistakes. Yeah. Definitely not. What are the only like terms up there? 4 and 22. There's no other C's. There's no other terms with a C in it, so there's nothing to go with that 33C. Aw. Poor little dude's all alone. 4 plus 22, 26. Minus 33C, that's all I can do. Because there's no more numbers, and there's no more collections of C's. There's no more like terms to put together. Yes?
I would be on a different question.
Sure, I think that one's good. Anybody else? Any questions about this here? This problem? You guys sure? You don't look like you're sure. If you don't ask, oh well. Yes?
I was just kind of, because I wasn't here Tuesday, and I don't know if I should have to go back through everything, but a ratio of 2 integers? I don't know, this is a question, but...
Well, give me a ratio to integers. What kind of numbers are integers? What are integers? Integers.
What is that? Isn't that the fraction?
Yeah, they're whole numbers and they're negatives.
Wow. So you're trying with that?
So did I tell you guys the story about the caveman and his rocks?
No.
So you got counting numbers. Counting numbers are what came naturally to us. Counting numbers 1, 2, 3. So we're cavemen, 1 rock, 2 rock, right? They probably had different language, but we translated it. So counting numbers are 1, 2, 3, blah, blah, blah. And I know we did talk about this a little bit because I talked about the whole numbers, and it adds the number that looks like a whole. And the whole civilization, the Babylonians were a civilization that did not have 0. They hadn't invented the idea of 0 yet. Yeah. So whole numbers are all the counting numbers plus 0. So the way we name the numbers sort of mimic the history of how we created them. And that, of course, you're alive today after a lot of this creation has happened, and you're sitting there like, how the hell would a whole civilization not know about 0? Well, because it had to be made up at some point. It had to be come up with. Right? So when they wanted 400 chairs, they would put a 4 in spaces and pray. Not really, but it's not too far from the truth. All right. Integers. So my little caveman, he's got 1 rock. He loses it, so he's got to come up with the idea of 0 rocks. Right? Then he has to borrow a rock, and when you borrow stuff, as we know, that means you're in negative territory, you're in debt. So now he's got to come up with the idea of negatives. You guys still with me a little bit? And again, this is just definitions. Guys, this is just definitions. We could, like we call the even numbers, we define them to be everything divisible by 2, blah, 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 blah. So this is just definitions. Counting numbers we define to be this. Whole numbers are that. Integers add the negatives. And then what we're really getting into in this section is rational and irrational. Rational numbers are the ratio of 2 integers where the bottom is not what? What can the bottom not be? What can it not divide by? No, you can't. Well, it's got to be integers. But which integer can I not use on the bottom? 0. Can't divide by 0. So it really sounds strange to say a fraction is a ratio of 2 integers, but it's not really. Give me an integer. Give me an integer.
5.
5. It's crazy. Now make it a ratio to another. Give me another integer that's not 0. 1. That's crazy. There's a rational number. Let me make another one. -3 is an integer, and so is 2. So what's another name for rational numbers? Anything that can be written as a fraction. A fraction is a ratio of 2 numbers. In fact, a fraction is an option for how to write a ratio.
So you can just write any number into there?
Well, dude, any fraction. Imagine a fraction, and that's a rational number.
So when the question's saying, like in the following, it says write as the ratio of 2 integers, if it's like 5, is it 5 over 1?
Which one are we looking at?
We're looking at number 1 now.
Oh, yeah, exactly. 5 over 1. Oh, I love it. That's why I said 5.
Yeah.
And that's why you look upset as you said 5, and I'm like,
Because I wrote it as 5.
does he have a history with 5? I don't know.
Yeah, you did it right then.
Yeah. Any whole number is rational because you can put it over 1, and that is a ratio of integers. Yeah.
So is negative 3 over 2 rational?
Tell me, is it a ratio of 2 integers? Is there a line with an integer over an integer? Yes. So it is rational. Anything that can be written as a fraction is a rational number. And we went over last time about a few other things. Yes?
So a number can be rational and whole and counting?
Beautiful. I tried to make it sound so whole. Every counting number is a whole number, except 0 is not both because that's the new thing. Every whole number is an integer because it adds the negatives. See, every step I take, it adds until I get to these guys. So every one of these is one of these. Every one of these is one of these. Every one of these is one of these, and then this is the trash pile. This is the weird ass stuff, right?
Okay.
Irrational would be everything that cannot be written as a fraction. Like square root of 2, pi with all those digits going around the room.
So as a write a ratio of 2 integers, that just means write a fraction.
Yes, write a fraction that's equal to that. So another possible answer for 5 is 10 over 2. Because that is a way to write 5 as a ratio of 2 integers.
Oh, that's what it's saying. It's saying,
Yeah, so 5 over 1, completely fine, but so is 10 over 2.
so when it says write a ratio of 2 integers, that means it wants you to equal the same number they're giving you?
Yes. Yes. So like 0.333 forever, is that written as a ratio of 2 integers yet? No, but we went over last time, and a lot of you came into this course knowing this. What is 0.333 as a fraction? 1/3. So I can write that as a fraction. So it is a rational number. In fact, we found out last time that anything that has a chunk that's repeating, you have a process, you go through that, you could make it into a fraction. So any fraction, let me write it down even, instead of just going slowly, because that means it's a note. Let me actually make it a note myself. This is all the fractions and decimals that stop or repeat.
I'm still a little lost on how to find what integer
We always put one
or
at the
ratio
bottom,
of
right?
the two integers
No.
they're wanting. Like if you a random decimal.
You're right. All right. So let me start off with a nice decimal. So see how I say decimals that stop or repeat. So there's one that repeats. That would be rational because you could actually find the fraction that it equals. Any decimal that stops, I can write as a fraction because that's a decimal is defined to be a type of fraction that is related to 10. But I can write it a different way because our number system is based on 10. So if I have 0.517, oh, poor little blue. How can I write that as a fraction, as a ratio of two integers?
5, 17, 1,000.
Yes, you.
Good job, Alan.
Yes.
Cool. Yes. Yes. Don't get too excited. This is something you should be able to do with no trouble. But I think it's just part of this is just the wording they're using. We got to realize that rational numbers is the technical term for it. But the key word of rational, the root word rational is ratio, which is what a fraction is. So rational numbers are anything that can be written as a true fraction. When I say true fraction, I mean there can be decimals in it. There can't be, I can put square root of 2 over 1. It's not a fraction because they have to be integer numbers.
So how would you do it if it was a negative then?
I don't know. Right? So how could I write 7 as a rational number? 14 over 2. Or 7 over 1. Or 777 over 111. Anything that is 7. But is a ratio of two things that is 7. That's it. That's all. Nothing special there. I mean, there really is nothing special there, guys. Part of this we know already. We should know this already for damn sure. Good. How to write that as a ratio of two integers. That's part of what we've been doing in a few different ways earlier this semester. I think what's new is kind of the terminology they're using, and you're making a little too much out of it. It's just, how do I make that look like a ratio? Well, the easiest way to make a whole number look like a ratio is to put it over 1. I mean, that's what I would do automatically. But if you want to make it a little more interesting, it could be anything that 7 over 1 is equal to. Because they're all 7. Okay. Sweet. Yes?
How would that be on the number?
Unrelated to this?
Yeah.
All right, real quick. Did you have a question about this?
I had a
Okay, Al, go.
It's
And then I'll come to you.
7.1, 17, and 18. They're both the same problems, but it's like, it's still word problem. I don't get it. Really.
Oh, okay. All right. So let's see. Wait. 7, 1, 17, and 18? Weird.
Yeah.
Well, 18 is I'm just going to let you write that. 18 is a writing exercise.
Oh, we don't have to. I mean, my bad. 16, 17.
Okay.
Sorry.
Well, let's look at 17. This is 7.1. Serena wants to open a licensed child care center. They'll only take care of licensed children. Her state requires that there be no more than 12 children for each teacher. She would like her child care center to serve 40 children. Now, that's kind of an evil number. What's a better number that's close to 40? I don't know. Let me see if you guys get a feel for this problem. The state says there are going to be no more than 12 children per teacher. 36 would be good, because then how many teachers would I need if I want to serve 36 kids? 3. So if I want to serve 40, considering that I can't chop people up, how many teachers do I need? 4. So what kind of work do you have to show? Kind of capture that. I mean, this is that this problem is kind of outside of this class. It's just, can you live in the real world and figure this kind of thing out? Yeah, so you guys try to force this into some kind of a, what kind of problem is? No. Just how would you figure this out? How would you figure this out?
40 divided by 12.
Yeah, sure. You could do that, and then you get this decimal, and you got to round up because
Yeah.
you can't cut people in parts. Or you could, but then, you make a show out of you, or you go to jail. Something. You're on HBO.
Yeah, today's day and age, don't say that. Yes, you can.
Let's see. Let's think about Dexter. That's right. How many teachers will be needed? Why must the answer be a whole number? Well, Oh, good. We didn't need you here, but we only need half of you. Chop. And it's like, bad. Oh, okay. Yeah, that's. I like this. This is just the exploration of numbers. It's not force it into a certain kind of thing. Yeah.
You say 40 divided into 12.
Well, sure. 12 into 40. Yeah.
You said 3. You said to 4.
Yeah, you better pull it up to 4. 3 is not enough. You guys see that? So this is not a problem that you necessarily try to categorize into a certain type of problem. You just figure it out. Use reason, right? Oh, you guys are like, I don't want to do that shit. Just tell me how to do it. That's too bad. This is the kind of thing that happens all the time. This is the kind of problem that happens all the time. And it's just rounding to make sure. I mean, if one bag of fertilizer covers 40 square feet, and I have 90 square feet, will two bags be enough?
No.
Well, no. So I'm going to buy 3 bags and have some. Okay. See, that's why it's called everyday math, because it's not quite categorizable exactly. We're not going to get to decimals because we can't say, I don't want this whole bag. Can you please just put some in smaller bags? The store's going to look at you like, who the shit are you? Get out of here. Right? I don't want this many potato chips. Can you please put share them with somebody? Get out of here. Right? Or, you understand what I'm saying? All right. Okay. Some of you guys think I'm actually yelling at you, but I don't know what to do for you. Okay. Anything else from the homework stuff yet?
If you were making the ratio of 2 integers, I don't know how else to say that. If you were doing the ratio of 2 integers on a decimal with, let's say, a higher number at the beginning of it, so basically a whole number at the beginning.
So like 2.78.
Yeah, anything like that.
Okay.
Would you write it out as 2,783 over 1,000?
Beautiful.
Okay.
Yeah, what is this? Tenths, hundredths, thousandths.
Yeah.
So it's 2,783 thousandths. And I want you to, if you don't like that, you can make this into a mixed number first. It's 2 and 783 tenths, hundred thousandths, right?
Okay.
1,000 times 2 plus that is that. We'll get there. That's not good enough because that's not a ratio of integers. It's a ratio of integers with an integer in front. That's not what they want. So you can convert it back into this real quick.
And how do you tell if the number is rational or irrational? Real quick. So here's the definition.
The base definition is if you can write it as a fraction,
Okay.
which is a ratio of 2 integers where the bottom is not 0,
Okay.
it's rational.
Okay.
Now, to make that more specific, because that's not good enough.
Right.
Because then you're like, well, how can I tell if it can be written as a fraction? So I had up here, there are any that are already fractions, anything that's whole number or something before that, right? Or any decimal that repeats or stops.
Those are all irrational.
Those are all rational. Irrational is like pi. Why is it impressive if somebody memorizes 50,000 digits of pi? Because it doesn't repeat. It doesn't have a pattern to it. Or not a repeating pattern anyway, right? So it's a real weird use of brain cells. Yes?
I have one quick question and then one I actually really need help on. Or I want to know about that. So the quick question is, you know how sometimes there's, like on the homework, there was like 3 decimals at the end, meaning the number repeats? Is that always going to be irrational, or can it be rational if there's a pattern?
So start over again.
So let's say it's like, no, like
It wouldn't
something
have the
bigger.
dots.
Let's say like 0.732458, I don't know, and then 3 dots. That's irrational, right? Because there's no.
Yeah, they didn't set up any reason to expect that there's any repetition.
But then if there's like, let's say 73, 73, 73, does that make it rational or no? Is it
Now, if they
just-
do this, whenever you write these dots, it means if there's a pattern, it continues. This is a little evil, but there is no pattern, so there's nothing to continue. And they'd have to be really specific that this whole thing would repeat. I mean, that's kind of evil for you just to assume that's true. Here, I can see they showed me some repetitions, and then this means it continues in this fashion.
So it's rational. I bottom one.
This would be rational,
Okay.
yes, because there is a repeating chunk to it.
And then I have my actual one from the homework.
And the top one's not?
The top one, did they write? Is that which problem is that?
It wasn't a problem. I just made up that number.
But it's like 7.
Oh yeah. I see what they're talking about.
Which is what he did.
I got you. But see, they represent the repeating with the bar, so they made it really clear. So when they write this, they mean there is no pattern, right? So it's like 3.1415 if it's pi, and then you put dot dot dot. There's no freaking pattern that's been set up, so that would be irrational.
Okay, and then the question I have on the homework is 7.3, number 132.
Okay. And real quick, if a rational number is anything that's already a fraction, or a decimal that stops, or has a repeating part, then irrational numbers are everything else. That would mean something like the square root of 2, which is 1.414, blah, blah, blah. There's no pattern to it. Any square root you can't do, square root of 7, square root of 11, any square root you can't do is irrational. And then there's pi. Some of you guys might know there's a letter E that's important in mathematics.
But like the square root of 25 is rational.
Totally, because that's a way to represent
Yeah.
5.
Yeah.
So square root of 25 is 5.
Yeah.
So it is totally rational. I like it.
So
All right, so where are we at?
it was 132 on 7.3.
Oh, yeah.
I just want to know ahead of time, are we doing the second tower? Because if we're not, I don't know.
What?
Like, well, just,
Yeah, not yet. I think I know what you're talking about. Not
you
yet.
got it wrong.
Oh.
You see what
I
I'm
see.
saying?
Guys, are these subtracting or are they multiplying?
Subtracting.
They're very obviously subtracting. So there's no multiplying going on. Right? So some of you guys might know, and that's what I was saying earlier, that FOIL thing I was talking about earlier. That's if these were multiplying, that's a way to get around that. That's not what's going on here. There's a 5m minus 3. And what's in front of the m plus 7?
Negative sign.
Negative. And if you really, really don't like this, what's always in front of anything? 1. So if it helps you out to imagine there is and not even imagine, just actually write it because it's there. It's always there.
Yeah.
What am I distributing through then? Negative 1. So here's 5n minus 3. What's in front of it?
Nothing.
1.
Oh, wait.
The positive one, yeah.
And does 1 change anything?
No.
No. So I don't even need those stupid parentheses. Stupid problem. But they just put it there to have this thing minus this thing. Are you guys cool with that? I don't need those parentheses. There's a 1. It's not going to change anybody. But here, what's going to happen when I bring the negative 1 through?
Minus.
Yeah, minus
M.
m minus 7.
Wow.
And then you just put your like terms together. Because I'm subtracting both of these. So I'm subtracting an m, and I'm subtracting a 7.
And we could put 1 in front of the M right there, right? 'Cause it's-
Of course, yeah.
Is the answer 4m plus 10?
I don't know.
Minus.
Yeah, 5m minus m,
Equals 4m.
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 Plus.
Negative 3 minus 7,
Minus 10.
minus 10.
Oh. Alright.
I'm
Cool.
not positive.
So, it's because we're adding the negatives. We're not multiplying, like you said. Or we're not
You're not multiplying those little packets, right? You're just subtracting them. So it's just combining that you have to do.
I don't
There's
know.
no
'Cause that confused me because it's -3 and -10. So in a way, I thought it would be a positive, but it's not multiplication.
But you owe 3, you owe 7, so you owe 10 altogether.
Yeah.
Yeah. You're combining, not multiplying. I like it. Yes?
I have a question on 87, 7.
No. 7.2? 87, the one about grants, or fundraising dinner? Is that the one?
Yeah.
I want you guys to really understand, there are no word problems in this class. There aren't any. There are problems with you're going to laugh at me. The problem with words. Word problem is where you come up with your own formula. Like a train leaves Wyoming going south 40 miles an hour. Another train. Yeah, that's a word problem. And I understand students all hate them, but they're the closest to real life. Except for, the guy that forgot how much money he put in the bank. But how much money you put in? This one is not, it's just a problem that's got a situation that you got to just know. Do I add these numbers? Do I subtract these numbers? What do I do with these numbers they're giving me? So grant is totaling up to cash. This is 87 and 7.2, page 620. He has 23 $5 bills, 18 $10 bills, 34 $20 bills, and another envelope he's got more bills. How much money is in the first envelope? So, again, this is a situation where you can overthink this. One envelope, or envelope, has 23 $5 bills, 18 $10 bills, and 34 $20 bills. That's in the first envelope. So the very first question is, how much money is in the first envelope? How do you do that? Yeah. If you had 2 $5 bills, how much money would that be? 10. So I got 23 $5 bills. You multiply. Yeah. Multiply, and then add all those up. See, that kind of problem is, here's a bunch of numbers in a situation. Do you know what to do with these numbers? Do you multiply them? Do you add them? Do you do a combination of those? But it's really hard as a student to not make too much out of something. Because you're like, I don't remember them telling me how to do this. No, just what would you do if you were this person? What would you do? You would put it in your pocket and walk out. No. Maybe you shouldn't do that. Don't listen. You would do this to figure out how much money there is. Okay. Maybe. I don't know.
Jeff is judges.
What's that? I haven't done this problem yet. But I mean, that's how you do it. That's more important than actually doing it, to be honest.
You just add it up.
Yeah, just multiply them out and then add them up. So 115, 180 is 295 and 680, 294. What'd you get? 295 and 680, 300 and 680, 975, right? Yes, okay, good. I mean, that's my one skill. I got to show off. Okay, anything else from homework stuff? I love that. That was a decent number of questions. I don't believe it. That's the way this should be. Okay. I think we effectively went through almost everything except the properties. So let's real quick review the properties remarkably quickly. As we talked about them plenty last time. If you weren't here, then okay. Catch up. So the properties. We've already talked about distributive.
And then you went commutative, and then you went associative.
Thank you, sir.
The first thing you talked about was whole numbers and integers.
Yeah, we already did that already.
No, but I'm just saying that's the first thing you went over.
Thank you. So distributive property I started there just because we already talked about it before that class. We know what distributive property is. These two are the ones that are really easy to confuse. Commutative and associative. Alright, so commutative. Alright, so let me give you a problem here. 7 times 3 times 4 equals. 7 times 3 times 4 equals. If I wanted it to be commutative, what would I have to write there for that to be that property?
7 times 4 times 3.
Yeah, commutative are where individuals do something. Individual numbers move. So the parentheses stay right where they are, so I can do this. To be honest, I could also instead, I could do this. I can move the 7 to the back. That would also be commutative. Right? Now to be associative, what has to happen? Parentheses associate. So they'd have to get up and come over here. That's associative. There are number systems and other kind of systems where that's not true. But for our number system, that's true.
These are just the definitions of what.
Yeah, this is what operations does this work for? It works for multiplication and addition. I like it.
I don't understand what the difference between that top and the bottom number you wrote is.
Nothing. Math-wise, they're the same number. But why can I say this equals this? What property of our number system allows me to say this is commutative property. How can I tell that's a commutative property? Because individual things commuted. What did you do to get here? You commuted to school. Individuals commute. That's how you remember it. This is nothing that I can explain. This is something I am defining. That's it. So don't try to see why is that true. No, we just defined it to be this.
I can't figure that out. Yeah.
This is a property that's true about our number system. It's not true about every possible number system we could have used. Now, I know I just said that sentence, but we're not going to suddenly start talking about other number systems. Don't freak out. But that's why we want to name these things, because there's something I can say about our number system. Our number system, multiplication and addition, is associative, meaning I can make parentheses move around. Now again, on another level, these are both kind of silly. They're both saying I can add and multiply whatever order I want to. Right? If I said 8 plus 7 plus 2, I would do 8 and 2 is 10, and then do 7 to make 17. I don't have to add it. I don't have to add it in the way that I was given them numbers. You guys understand that? You can add a string of numbers in any order you want to, or you can multiply a string of numbers in any order you want to, and you'll always get the same answer. Are we all cool with what I just said? These two properties say that in two different ways. Yes, sir?
You also said that, like, with commutative, work with multiplication and addition, right? That's what you just said? Yeah.
Yep, that's what I just said again.
I'm just
Yeah.
reiterating new examples.
Thank you.
Whole class pick.
Oh, thank you. Yeah. For anybody else that wasn't listening a second. Yes?
What difference by number 2 and 3? Same number.
I know. Okay. So, the numbers are the same. The problem would not say simplify. The problem would say, what property is this? Why is this commutative? Because what moved? Individual numbers.
Right, okay.
What property is this? Associative, because parentheses got it. Parentheses associate. Individuals commute. So if I have A plus B plus C, and I want to use associative property, the good old ass property, what would I do?
You can change the parentheses.
Put the A and the B in the parentheses.
Yeah, exactly. Bam.
You want to
So they got up and moved there.
Okay, and then commutative, that would be just.
And if I wanted to use commutative,
With the C and the B inside.
Gotcha.
it would be what?
A plus C.
Plus C.
Yeah, C.
Or you could do,
That one's just confusing because it looks like they moved the parentheses.
this guy went there.
I know.
Individual moved.
It's just.
I know, I'm with
Oh,
you.
yeah,
So that's
you
why
can't-
I always say
yeah.
that one's second, because that's the one that looks a little weird.
Oh, okay, because you can't
I'm with
move
you.
the. Okay, gotcha.
Are the parentheses around anything else than they used to be? All right, then they didn't move. Bang.
Yeah, that's right, yeah.
They didn't.
Yeah, okay.
Yeah.
So when you have like 2A, you just separate the 2 and A. That's the answer.
What's the question? Is this from the homework or?
We're thinking too hard into it.
Yeah. If I had 2 times A, and I said use commutative property, this is where it's going to look weird, but it's still true. 2 times A, if I use commutative property, how could I write that again?
You can't.
I can.
Oh, you can't?
Yes, 2 times A is the same thing as A times 2. Now that looks weird, right?
I messed up.
That should look weird. That hurt me a little bit to write this. Technically it's true, but we just always put the number out front as a coefficient, right? But technically this is true. Yes?
You do not put a parentheses if there's not a third. Or like,
You don't.
I could if I wanted to.
I don't like it. That one I don't like.
Oh. Alright. No, I kind of like that you don't like that because we're so used to writing these things as this. But technically this is true also.
Why
Of
you
course.
didn't do something like that on the test or something?
Probably not that one.
Well, you'll probably ask which one's.
Maybe now I will. Huh?
You'll probably ask which one's associative, which one's.
Yeah, that's what I normally do. I give you a series and I say, name the property illustrated.
Yeah.
So I'll put something like this. Now what property is this, obviously? Uh-oh.
Well, you have to put the
There's
parentheses.
not just 2 properties, there's 3.
X plus.
So which property? What did I just do? What did I do from here to there? Okay, thank you. That's distributive property. There's distributed. And then we talked about commutative and associative, but there's 3 properties, right? All right, that's obviously distributive. The instruction would say, name that property, one of the most boring game shows in history, but right? But then I'll have somebody that solves this. The instructions don't say solve, they just say name the property. That's all they say. So watch for that. Don't do what the instructions don't say to you. That test was long. Well, you made it long. I don't know what to tell you. Yes?
Can you give an example of associative? Like on that.
Distributive.
All right, so here.
That's the associative.
No, that's commutative.
Oh, down here?
Oh, and
Oh, that's X plus 3, X plus, no, that's, that's associative.
Yes.
What is it?
Because you,
I think I got more people on the associative side now. It's totally associative. Did 4x35, right? 4x35. Did any individuals move? No. What moved? The parentheses got up and moved over there.
You're right.
Yeah. Well, I better be, or else I have to go.
shit, I had it wrong.
He said that else I think.
Yeah. And you know, obviously, what would this be? That's probably going to be, I mean, I don't know.
Yeah.
But why? What is this? An example of? Did the parentheses get up and move? Nope.
No.
Still exactly the same stuff inside, but the stuff inside, the individual stuff inside. So that's commutative. Okay. That's commutative. Parentheses did not go anywhere. They're still right around the x and the 3. They didn't go anywhere. The x and the 3 switch spots. That's all I'm going to say about that. That's all I'm going to say about that. Because it is a little confusing, but it's also... totally blunt is not as important as some of this other stuff.
I think, like you said, it's just like a rule. Like,
Yes,
they were
it's
not
just
trying
a
to-
rule. It's just it's not really a rule. It's just an observation of how our number system works.
How it's done.
Yeah, and there are other number systems we could have used that don't have some of these, to be honest, or other operations.
Yeah.
Okay. Oh, I think that catches us up. Oh, we talked about, what did this mean? Identity. Things that can be stolen, Alex. No. Well, yes, but mathematically, What's the additive identity?
Anything plus a number.
No.
Zero, wait, zero. You can have zero.
And then you put
You can have zero, and it's the same number.
0 is the additive identity.
You also have
Multiplicative is
Yeah.
Multiplicative is not.
Is what again? 1. I like it. Hey, let's do this. Let's everybody put the phones away. Ooh. Thank you. Especially people that should be paying a lot of attention. So why do we call this identity? Because when I add 0 to something, it doesn't change its identity. Right? And when I multiply something by 1, it doesn't change its identity. It doesn't change what it is. So let that, and again, it's just a definition, and it's an observation of what happens. What happened? Identity, additive identity is 0. Multiplicative identity is 1. Cool. I like it. Listen, as I write, it makes it easy. Inverse is, now I have to first define, I'm going to say that to you. I have to first define identity to make inverse make sense. An inverse, an additive inverse would be something that would take it back to its identity. Right? So what would I add to 7 to bring it back to 0? Negative 7. So the additive inverse is just the opposite sign of the thing. So what would negative 4/5 additive inverse be? Positive 4/5. I like it. So the multiplicative inverse is something that I would multiply by to bring it back to 1. It's kind of like the two different ways you can cancel stuff, right? So multiplicative inverse, if I have, for example, 4, what would I multiply 4 by to get it to be 1? 1/4. I love it. I always have somebody say, you wouldn't multiply by somebody, you would divide it by something. So, okay, 4 divided by 4 is 4 times 1/4. So what's another name for multiplicative inverse? Reciprocal. So that'd be 1/4. What's the multiplicative inverse of negative 3/8? Negative 8/3. You don't change the sign, because if you did, it wouldn't come out to be 1. It'd come out to be negative 1. You just flip it. Yes?
For the one on top, would you put a 1 on here before
I mean, if you needed to. Yes. No, it doesn't need that to work. Some people need that to see how it works. But it doesn't need that to work. No.
Just to show your work.
Yes. Well, just to show yourself what's happening. Yes. So you could put it over 1 so you can see that's top, that's bottom. Sure. Yeah. Okay, cool. So that brings us up to date. That's where we left off last time. Okay. So today we're going to talk about systems of measurement. Let me see what you guys know already about some stuff here. Where do I start off? I'll tell you what, I'm going to start. Yeah, okay, we can start this way. No, screw it. I'm going to start with the metric system. I'm going to do this out of order. Just because.
Which chapter is this?
7.5, section 7.5. So we're closing out chapter 7. What do you guys already know about the metric system? Can somebody tell me some unit of measure in the metric system? I bet you can. Looking at me. Huh? Meters. What else? Maybe smaller. Centimeters. Tell me, please tell me. Everybody's heard of that. If this is not your country that you were born in, you probably grew up with. In fact, we are now officially the only country left on the face of the earth that does not use the metric. There used to be 3 countries. The other 2, one adopted and one I think is in the process of adopting the metric system. Americans, holy shit, we're never going to go there. We just aren't. I like my gallons. Well, all right, whatever. All right, but what's so great about the metric system then, Jeff? What's so great about it?
Nothing.
Oh, that's funny. Yes.
Kilometers metric?
Yeah, kilometers. I like it. So notice what's happening there. You got meters, centimeters, kilometers or kilometers, right? There seemed to be this root of meter. And also when you go to buy soda, that's the one place we use metric. You buy liters of soda, right? So you could have kiloliters, centiliters, liters. Okay. Are you guys semi with me? So the way that we have inches, feet, yards, miles, completely different, right? And the conversions are all different between any of those. How many feet are in a yard?
3.
3 feet in a yard. How many inches in a foot? 12. How many feet in a mile? 5,280. Now you got to know on a ruler, how many inches are on a ruler? 12. I'm going to have to smack some people. No, just show. So if you get a ruler, mine's been through a little bit. It's got 12 inches on the bottom. It goes up to 12. And on the top, it goes to 30 point something or other centimeters. All right, so conversions between our freaky ass system and the normal metric system are going to be very strange. Right? In fact, I don't know if you guys realize this. This isn't exactly completely 100% true, but it's got a kernel of truth. Our number system, our measurement system, is based on the measurements of a king of England. Yeah, so we had the Tea Party, not, the political party, but just thinking of history where they threw the tea into the harbor. And then we had the revolution, but we're like, we'll keep the weird-ass measurements of the king. Because, of course, the king was given by God to the people. I'm not going to do a history class. Right? And for some reason, we kept all that shit. Right? The foot was actually held, and so forth. I mean, all right. Whatever. But metric has, let's think, normally the biggest one we know about is kilometer, for example, for length. For volume, it would be kiloliter. And of course, you guys know if you watch enough, CSI or some kind of crime shows.
Law and Order?
Sure. Where they have drug busts and stuff.
CSI Miami?
That wasn't. This isn't really a game show where you're trying to win money. Kilograms, yeah. So grams is for weight. Liters is for volume. Meters is for length. Then there's 2 more here that people normally don't know, and I don't blame you too much because we don't use this. Kilo. Anybody know what kilo means? He's got 3 kilos.
Yes.
1,000. Don't worry about it. Don't worry. They didn't get any money or anything. So thousands, right? So thousands, hundreds is something, tens is something, and then you have 1. So this will be meter, liter, gram. So if I have 1,000 kilometers to go, that means if I have 1 kilometer, that means I have to go 1,000 meters. If I have 1 kiloliter, that means I have 1,000 liters. So forth. Notice what this seems to be based on. This number system seems to be based on 10. This measurement system, because our number system is based on 10. That's what's so good about it. That's why scientists use it. The one time that a group of scientists didn't use it, I don't know if you heard about this. I think it was the Mars Climate Observer. I can't remember which one it was. They shot it off towards Mars. One group was using our units, and the other group was using metric. And they were like, okay, we're approaching Mars, and we've crashed into Mars because we didn't measure the distances correctly. Do you understand what I'm saying? Yeah. One group said 4, and the other group thought they meant 4 feet, and it was really supposed to be 4 meters. Are you guys understanding? So, of course, scientists always are supposed to use metric because most of the world does so that everybody can communicate correctly, right? So that kind of thing doesn't happen. Thankfully, nobody was on board. Then we have, right under here's another one that people normally don't know, and again, I don't blame you. And then we have the 2 that we normally do know. There's centimeters, and then what's even smaller than that? Millimeters. So like centipede, millipede. For the number of feet down there. So centimeters, centiliters, centigrams, and then you have millimeters, milliliters. Milliliters you should be roughly used to if you have kids, especially at the little, give them 5 milliliters, the little thing that comes with the cough medicine. Yes? Okay. That's another place, the one little tiny place you see metric. Yeah.
I have another play. Well, I don't know if this is the same, but it sounds familiar. You know about like horsepower to kilowatts? Is that a
Yeah, there you go. Horsepower is a really freaky unit, right? And then kilowatts is the accepted kind of way to measure power. Yeah. All right. So let's fill in these things that we don't know here. Has anybody ever heard of hectometers? You might have heard of hectare, if you deal in real estate, possibly. It's related to acres. And then you've got deca. So you got kilo. Don't worry, I've got a little handout with this stuff. Hecto. Deca. Kilo means 1,000. Hecto means 100. Deca means 10 of something, right? So decameter means 10 meters. And this is 1. This is meter, liter, gram. This is 1. And then you got this little dude. Now, if that's like a whole number, you guys see what I mean by that's a whole number? This is like 1,000, 100, 10, 1, and then that's below that. What would that be? That would be the first, what kind of number?
Negative.
Not negative. It's on the other side of the... So I go 1,237, 1,237 point. So this would be the first, what kind of number? Decimal. So it's decimeter, deciliter, decigram, deci. Makes total sense if you let it. Right? So that's the prefix for that is deci. So if I said it's a decimeter away, that is 1/10 of a meter away. That's what deci means, 1/10 of something. So it mimics our number system. Thousands place, hundreds place, tens place, ones, 1/10, 100th, centi, percent. Holy shit, right? Centimeter, 100th. So this is centi, and then milli is 1,000th. Now there are more in both directions. I don't know if you ever watched Back to the Future where he's like 1.1. He says gigawatts, and that was actually because they didn't know how to pronounce giga. It's supposed to be gigawatts, but they didn't know how to pronounce it when they made the movie, which is kind of funny. Back to the Future? No? Yes?
Yeah,
I know it was back in the 80s before some of you guys were born, but you know. I watched like Metropolis, shot way back. Way before I was born. Okay. Now watch. So there's stuff like gigawatts. There's stuff down here for like femtometers and stuff that really like the length of a human, the width of a human hair, or the distance between atoms and something. You're getting really stupid small, or you get the distance between stars, or the yield of an atomic bomb. That's where you got to use these crazy big ass numbers. So there's more out there, more down there, but these are the core everyday ones.
But there are even like a light year.
Oh yeah, of course. You could use light years also.
What is a light year?
Well, a light year is the distance that light travels in a year. Yes. So, for example, it takes it about a little more